Welcome to a new video. This video is going to help us to explore graphing quadratic functions. So we're going to start off by graphing the equation y equals x squared. So this is the simplest quadratic equation that we can possibly graph. Quadratic is a fancy word for the fact that this is a squared. And so if we don't know how to graph something in math, what we do is we plug in numbers and make a table of values. So I have selected some values here to plug in. I picked things that are close to 0. I picked integers, and if you don't know what to pick, that's a good place to start. And if that isn't enough to know what the graph looks like, you would just keep picking more and more values until you have a good idea. So starting with the easiest number to plug in, 0, I would do y equals 0 squared. 0 times 0, which is what 0 squared means, is 0. So I'm going to put a 0 right here. And then I would do y equals 1 squared and say, okay, 1 times 1 is 1. And then I could do y equals 2 squared, and 2 times 2 gives me 4. And then I'm going to do the same thing the other direction. But this time there's an order of operations thing happening here that we have to be careful about. When we plug in a -1 for x, we actually need to think of that as though it's in parentheses being squared. -1 squared is -1 times -1, which is a positive 1. When we plug in things to x squared, it actually makes them all end up being positive. So when I do that with -2, -2 squared is going to be a positive 4. Now, for my students doing this, we've actually already graphed this before, and so there are some things that should not be surprising about how this graph looks. This goes up in either direction, and it's curved as it goes up. And it is a little tricky to draw on a computer, but I actually feel like that went pretty well, if I'm being honest with you. So this graph is called a parabola, which goes over here in this blank. The highest or lowest point of the graph is called the vertex. So we've got some vocabulary happening over here that's going to help us talk about parabolas and quadratic functions, where we all know what we're talking about. So highest or lowest point of the graph is called the vertex. So in this parabola, the lowest point is called the vertex. It doesn't actually have a highest point because it goes up forever and ever. And we represent that with these arrows. The coordinates of the vertex, so this lowest point right here is 0, 0, which is also known as the origin, but the coordinates are 0, 0. Something else that we could say about this is which way does the graph open, up or down? And there's different ways you could phrase this, but this is kind of a way that mathematically we've all decided to talk about this. This graph opens up because the part of this parabola that is coming out away from each other is at the top, not at the bottom. So if you want to think of it kind of like a cup, maybe that's easier. It's a cup where the opening is opening up, versus if the cup was upside down, then the opening would be down instead of up. So it opens up. More vocabulary, we call y equals x squared the parent function of all quadratic functions. And this is probably, if you're new to quadratic functions, this is probably the first time you've heard that phrase. Parent function means it's the simplest kind of quadratic function we can have. All other quadratic functions can actually be considered children of this graph, to kind of continue the analogy that parent graph suggests. So this is all the rest of ours that we're going to look at on this video. We're going to relate to this graph, and we're maybe going to move them around, maybe change their shape a little bit, but we're going to do that in an interesting way, that we're going to see the connection between the equation and the graph and things like that. So I'm going to scroll down to our next one. Okay, so we're going to do the same thing, but we're going to graph y equals -x squared. I'm going to try making this a little smaller, and let's do blue. Okay, I'm going to graph y equals -x squared. So this is going to start off really similar, And you might actually already have an idea of what's going to happen. I don't like that after all. Because that negative is going to do something. This negative in front of x squared is going to do what maybe you would expect it to do, depending on how intuitive you are. We're plugging in the 0, but 0 squared is 0, and then I make it negative. Well, 0 can't be negative, so it's still 0. When I plug in 1, then 1 squared is 1, but then I have to make it negative. Another way to think of this that might be helpful, I don't know why the tablet keeps combining my equal signs, so I'm sorry about that. Another way to think of it is there is a 1 in front of the x squared that we don't actually write because we've simplified things as mathematicians, but if we want to put it back there, it makes it a little bit more obvious. What we're doing is we're squaring the x and we're timesing it by -1, and order of operations, or PEMDAS, tells us to do the exponent first before we multiply. So we're going to do 1 squared and get 1, but then we're going to make it negative. And it might be that intuitively that makes sense. If I make the original graph negative, then all of my y values are going to have to end up being negative. So the same thing happens here with 2, that I would do 2 squared and then I make it negative, so I get -4. And maybe you're on board with that, but you might run into another issue when we start playing in this negative. So when I plug in -1 and I square it, that becomes +1, but then I make it negative. And what you can't do is you can't say, oh, well, those negatives should cancel out, right? Because the squared is actually going to affect this -1 before we could even interact with the negative on the outside. So again, PEMDAS, order of operations, you do the exponents before you do the multiplication. And this negative is really acting like multiplication. So when I do the -2, the same thing is going to happen. And so -2 squared is 4, and then I make it negative, and I get -4. So if I graph this, still got 0, 0, but now my parabola is going to open down. And it turns out that this is something that's going to be consistent for us, is that if we have a negative in front of x squared, our graph should open down. So over here on the side, I've asked some questions. What's similar about these two graphs, meaning the first graph, y equals x squared, and this graph? And you can see a little bit of the graph over here at the top. But like if you are looking between the two, here's our first graph. We almost actually can see them both in the same kind of frame. We can see most of them in the same frame. They actually look pretty similar. And if you look at the table of values, they look really similar. The real difference here is that one is positive and one is negative, which makes one open up and one open down. So some things that are similar about these two are their vertex is the same. So that's similar. And another thing that's similar is that they're the same shape. The amount that the first graph is going up, how quickly it's going up, is how quickly the bottom one is going down. So they have the same shape. And so the thing that's different is that it opens down instead of opening up. So this graph is called something in particular. So this is where we're going to learn some more math words for what's happening. We could describe it maybe some different ways. Like we could say that the graph flipped or the graph is upside down. But our math way of saying this is that this graph is a reflection. Kind of like in a mirror. When you reflect something, it turns over to the other side. In mirror land, I don't know. This graph is a reflection of the parent graph across the x-axis. So the y-axis is the up and down one. So it's not that we flipped it over the y-axis, we flipped it over our horizontal axis, which is the x-axis. So we're going to explore some more similar ideas here about what else we can do other than just flipping it over. Can we move it? Can we make it change shape? And so we'll see how does putting numbers in different places in our equations change how the graph itself looks? And is it something that we can predict so that we don't always have to make a table of values, which would be nice. Okay, so the next one we're going to look at, we've got y equals x squared, but now we have a plus 2. So one of the ways that we can be good mathematicians is we can actually try to predict what might happen to see if we're right. And if this is, again, if you're in Algebra 1 and this is your first time experiencing quadratic functions, it's okay if you don't predict correctly. What's important is that you learn from what happens. So let's say that we just have no idea what's going to happen. Let's plug in these numbers and see. And we do need to, of course, make sure we're paying attention to order of operations. So here we've got an exponent and we've got an addition symbol. And so exponents come way before addition. So we're going to do 0 squared and get 0, and then we're going to add 2 and get 2. And so now if we compare that to the first one, we might start to already see what the pattern might be, that what's this plus 2 going to do. So if I plug in 1, well, I need to do 1 squared, which is 1, then I'm going to add 2 to that and get 3. And then I'm going to do 2 squared and then plus 2. So 2 squared is 4. When I add 2, I get 6. Now, if I look at this and compare it to the numbers for my parent graph, which I'll just rewrite over here to the side, what do you notice about them? They're all 2 higher than they were before, because all we're doing is the same thing where we plug in the number, but then we are adding 2. So that means this should be 3 and this should be 6. Also, if you didn't already notice, we've got some symmetry happening here. So the graphs of these are symmetrical because if you cut them in half along the y-axis, they're the same on either side. But that means the table of values is also symmetrical, that if our vertex is the thing that's in the middle, then what should happen on either side is that we should have similar numbers. So the 2 closest numbers were 3, and the 2 that were next closest were 6s. And if we kept going, if we plugged in 3 and -3, those should be the same. So if I graph this, I got -2, 6, -1, 3, 0, 2, 1, 3, and 2, 6. So here is my parabola. That is a U-shaped graph. That's what a parabola is. So let's compare this graph. Again, we're comparing with the first graph. We're not gonna keep comparing it to the one right before. We're gonna keep going back to the first graph, which is our parent graph. So what's similar about them is they are still the same shape. And there may be some other things that we could say are similar. They have the same, we call it axis of symmetry, which is where we would put a mirror to show that they're the same on either side. But the main thing that I want us to see is that they are the same shape, because what's different is their vertexes are different. But more importantly, well, no, I guess that's what's important. The vertex is different. So it's the same shape. It's just that we've moved it. It's moved to a different place. And so that's changed the vertex. So I guess I could have left that comma there. We could say it's in a different place. So the mathematical way for us to describe that is that the graph has been shifted up 2 units. Another way that we could say this is we call this a translation. Okay, so we've shifted the graph up 2 spots. That means its vertex is different. All of the points actually are in fact different. But what it's done is it's still kept the same shape. It's just that we've moved everything up 2 units. And now we can see that, oh, the equation said +2. So maybe we can then come up with some conclusions about what adding 5 would do, or adding 7, or things like that. So let's look at a new problem. this time we have y equals x squared minus 3. Now, many of you can probably thinking, I have an idea what this might do, but it's also okay if you're not thinking that. We each have our own math abilities, and it's fine whether it takes you 2 seconds to understand something. It's also fine if it takes you 2 minutes or 2 hours or 2 years. We all learn at different rates, okay? So this minus 3, we're again going to do after we square. So whenever I plug in 0, I'm going to do 0 squared, and then I'm going to do the minus 3. So 0 minus 3 is negative 3. And I'm going to do the same thing with the 1, and then have 1 minus 3, which is a negative 2. And I'm going to do the same thing with the 2. And if you are in a class that allows you to use a calculator to do these sorts of things, you just want to make sure that you type it in exactly how I'm writing it here. And when you plug in negative numbers like negative 1 into the calculator, you need to put them in parentheses so that the calculator will actually square negative 1 instead of just 1. So keep that in mind. But it really is almost easier just not to use a calculator. It's almost faster. And it's good math skills. So negative 1 times negative 1 is positive 1. Minus 3 gives us negative 2. And again, if we've noticed as we've been going along, or at least I think I've said this, the numbers closest to this middle should be the same, and then the 2 numbers that are next should be the same. So without actually plugging in negative 2, this should be 1. Now, what I recommend is especially if you're on a quiz or a test or something where it really matters that you're getting something right, that you go ahead and plug them all in, because then if you aren't getting things that match, then it clues you in that you've got some sort of problem that you need to figure out. So let's graph these. Negative 2, comma 1, negative 1, negative 2, 0, negative 3, 1, negative 2, 2, 1, and then we draw our parabola. So compare this graph with the first graph. What is similar? So comparing it to y equals x squared, which had a vertex at 0, 0. But one of the things about that graph, and so I'll just draw real quick what it looked like right here so that we can remember in a different color, is there's a pattern to how these keep going up and over, that the first 2 points are up 1 and over 1, and that's true here as well. And then the next 2 points, you can count them from these new points I've drawn, or if you count it from 0, I think it's a little easier because then you're using 2 and 4, which 4 is 2 squared. So we go out 2 and up 4, and that's where this next point is. And then we go out 2 and up 4, and that's where this next point is. And if we wanted another point, if we had room, we'd go 3 and 9, and then 4 and 16, because those are perfect squares. And the same thing is happening here with our new graph, that I have to go out 2 and up 4 to get to this outside point. I have to go over 1 and up 1. There's this pattern that's happening, and that's what's causing these to have the same shape. We could say that they're going up at the same rate, even though one of them is starting out higher or lower than the other. So what's different about them is that they have different vertexes. Technically, the plural of vertex is vertices. So if you're thinking you're going to make fun of me for saying vertexes, I apologize. This graph, our technical language for it, this graph has been shifted down 3 units. And so the idea would be that now maybe we can look at equations that have a minus something, and we can say, oh, well, I know it's going to have that same pattern where I'm going up 1 over 1 and up 4 over 2, either direction. I know it's going to have that pattern. I just know it's going to start at a different place. So now you could try to graph y equals x squared minus 10 and see if you can put it in the right place. And you can always use a table of values if you want to, either to check yourself or just to graph it outright. But that's the connection between the equation and the graph itself. So let's look at a new problem. Okay, we have y equals x plus 2 squared, and our x plus 2 is in parentheses. So this is going to actually do something different and maybe something that you wouldn't expect it to. And I did not actually fill this in with -2, -1, 0, 1, and 2 because, spoiler, those might not actually be the best things to use. If you are going to be the type of person who, when writing this down, will get really angry if you have to write them down out of order, then don't write them down until after we're done with the table. If you don't know what to plug in, like if this is your first time graphing something like this, you should always start with something that's really easy to plug in, like 0. And so I would put 0 where x is, and I would use order of operations, which says do the parentheses first, so do what's inside, which is 0 plus 2, and then take that and square it. So 0 plus 2 is 2, and then I'm going to square it, and that gives me 4. And so far we don't really have a lot of information about what's happening here that might be different. So we need to keep going. Let's try plugging in 1. So 1 plus 2 squared equals, well, we got to do the 1 plus 2, which is 3, and then square it, and that gives us 9. So we've run into an issue. 9 does not fit on this graph, although I can pretend like it does. But what do you think is going to happen now if you plug in 2? 2 is going to go even farther off the graph because when we plug in a bigger number into our parentheses here, it's giving us a bigger number as an output. So it doesn't actually help us to plug in 2. We actually need to now look at our negatives because 3 is not going to help either, and 4 is not going to help. We're just going to get bigger and bigger numbers. So if I plug in -1, I would say -1 plus 2 is 1, and 1 squared is 1. So at -1, I'm at 1. Still don't really have enough maybe to know what's going on, so I'm going to keep going. Plug in -2. And so -2 plus 2 is 0, and 0 squared is 0. So -2, 0. And then let's go ahead and plug in -3. So -3 plus 2 is -1, and then I square -1, and remember the -1 itself is being squared, so -1 times -1 is a positive 1. This is the point where maybe, if you haven't already, you would start to kind of be like, okay, I kind of see what's going on here. But if not, then we could keep going and we could plug in another number, because 1 and 9 didn't really work out very well for us because it was off our graph. And it's not close enough to the vertex. As soon as we get this point where we've turned, that implies that this is my vertex. Okay, because it turned around and I've got some symmetry already happening here. So really, without even plugging in -4, I could look at this and say, well, at -4, it should be up here at 4 because that creates symmetry with these points. And then if we wanted to, we could go farther and say, well, at -5, it should be 9. But here is our graph, and let's think about how this compares to our original graph, which started off here. Okay, we still have the same shape. We have the same pattern happening, that we're up 1 and over 1 from the vertex, and then we're up 4 and over 2 from the vertex. But what's different is that our new parabola has been moved to the left 2. So what's similar is, again, that they have the same shape. But what's different is that the vertex has moved, and really the whole graph has moved, but the vertex, if we want to put it simply. And so this whole graph has been shifted left 2. And so you actually can know that based on the fact that we have a +2 that's inside parentheses with our x. And so there's this cool thing that we can use to understand this. When we see a plus 2, we might think, once we know that that's going to move left or right, and the reason it makes it move left or right is because it's directly affecting the x before we square things. So it's actually making things move left or right, the x direction, before we have the actual function itself, which is a squared, happening. But the way that you might think, once you know that it's moving left or right, you might think, oh, plus 2, that should move to the right too, because that's the positive direction for x. But there's actually this thing in math where anything that is in parentheses like this, when we're talking about graphs, is part of the super secret opposite society. I'm not sure why I'm choosing to write this out, because it's going to take forever. Super secret opposite society. And the super secret opposite society has a very simple rules that when you have a function that you're graphing, if the number is inside of your parentheses, then that means that whatever's happening is the opposite of what you would normally think. So because it's a plus 2, we want to think the opposite, which is negative 2. So we want to think that means it's shifted left. And that's going to be true also if this said x minus something, which is what we'll graph next. So I want to suggest to you that we could start actually trying to graph some of these without having to make a whole table of values. So if we understand on this next one that the minus 3 is inside, and that the minus 3 being inside means that we're going to move to the right 3. If we understand that and we know what our pattern is for parabolas, that we normally have a vertex at 0, 0, right? It's normally here. We're going to move it over 3 spots, and now here is our vertex. Normally, from our vertex, we go up 1 and over 1 both directions. So here's where our next point should be. And then from our vertex, we normally go up 4 and over 2. And so if we know the pattern and we know what the equation is trying to tell us is happening, then we can graph this without a table of values. Now, if that's not working out for us, we could totally plug in points. The easiest points to use would be 1, 2, 3, 4, and 5, because that gives us the 4, 1, 0, 1, and 4 that we know and love, because we keep getting those numbers over and over again. So this is the same shape still, but the vertex is different, and this graph has been shifted right. So just to make it clear here, the equations follow these rules that tell us what's happening. So so far we've seen that a negative in front is going to flip the vertex so that it opens down instead of opening up. We've seen that having a plus or a minus that is next to the x squared but that there's no parentheses, we've seen that that means that it's going to move up or down. A plus 2 made it move up 2, a minus 3 made it move down 3. And now we're seeing, okay, if there are parentheses, then that's going to make it move left or right, the opposite way of what the sign is telling us would normally happen. So if we know the pattern and we know what these equations are telling us, we can graph a parabola really quickly. If we don't, it's okay. We can just use a table of values and get by, and that's totally fine. What's really cool about these rules, though, is that they actually work for a whole lot of different functions. And so you might think, oh, well, I'll just get by because it's just this one thing we're doing in math. Well, we're doing this in Algebra 1, and you'll do this again in Algebra 2, but in Algebra 2, and then in pre-calculus, you'll talk about doing it for all these different functions that at this point in your life, you've probably never even seen or thought about. So that's why it's helpful to actually try to do it this other way where, yeah, maybe you use a table of values, but maybe you try to figure out what's going on without the table of values. We've got 2 more graphs to look at. And so what we've done in class, we've actually kind of already looked at a graph like this. So y equals 2x squared. If we plug this in, order of operations says to square and then multiply, kind of like what happened with the negative earlier. I want to square 0 and get 0, and then I want to times by 2, and then that's still 0. Or if I have my original table of values memorized, the 41014, I just need to multiply all of them by 2 because I'm still going to square first and get the original answer, but then I'm going to times it by 2. So either by, making some logical leaps, or by plugging in all of these numbers, we should in fact get 8, 2, 0, 2, and 8. So 8, 2, 0, 2, and 8. And what we should notice about this parabola, because we're being asked the same questions that we were before, what's different about this is not the vertex. The vertex is actually what's the same. So we have a similar vertex, and it still looks like a U-shaped graph. It still opens up like our original one did, but what's different about it is its shape. The way in which it's going up doesn't fit our same pattern. It's not going up 1 over 1 like it was before and up 4 over 2. It's not doing the same thing. It's actually going up faster. We could also say that this graph is narrower. That's a word that we could use to describe it. We could also use some other words like skinnier or things like that, but narrow is a pretty good word for this. It's narrower than our original graph. So our math way of saying this graph is a vertical stretch by a factor of 2. And the reason we say that is because what we're doing when we multiply all of these by 2 is we're taking these points that we originally had that I've got drawn in gray here, and we're actually taking them and moving them twice as far away from the x-axis as they originally were. So this point 1 is twice as far away and is now at 2. The point that originally was at 4 is now twice as far away and is at 8. So every point ended up being twice as far. So we've taken our graph and we've stretched it. Like if you can think about taking a hold of these points, we've just grabbed them and pulled them up, stretching them. And that's by a factor of 2. Now, what did that was the fact that we're multiplying by 2. So addition and subtraction in different ways moved us up, down, left, or right. But when we multiply by a number, that's going to actually affect the shape, how fast it goes up or down. And having a number like 2 or even 3 or 4 or 5 is going to make our graph go up faster, which makes our graph narrower. Whenever we instead have a fraction, something a little bit different is going to happen, because here having to multiply by a third is actually similar to having to divide by 3. It's actually the same thing as trying to divide by 3. And so whenever I have to figure out, what is 1/3 times 0 squared, I'm going to do 0 squared and get 0 times by 1/3 and get 0. That's pretty easy. 1/3 times 1 squared. Well, I do the 1 squared, which is 1, and then times by a third, and I get 1/3. I'll get 1/3 here as well. So you'll notice I put 3's here instead of 2's, because you can do it with 2, but it makes things a little unsatisfying. So I picked 3 because I knew that when I do 3 squared, I get 9, and that's actually divisible by 3. So I get 3 instead of having to have another fraction. Now, fractions aren't as bad to graph, at least in this case, as you might think. We're going to graph 0, 0, and then when we graph a third, it's a point that's a little bit above 0. And then make sure you skip over 2 and go to 3, 3. And so what's happening here is our graph is wider than our original graph, because this time our points are all a third of the way they originally were to the x-axis. So here's where our normal points are. Well, I guess this one would have to be up here that I'd have to be showing off. Okay, our points are a third of the way away from the x-axis that they were. Here they're at 1 and 1. I'm only a third of the way to 1. here where they should have been at 9, because 3 squared is 9, I'm a third of the way to 9, which is 3. So in a similar way to the last one, what's similar is the vertex is in the same place. We didn't move left, right, up, or down, but what's different is the shape. That this time we didn't go up faster, we actually are going up slower. And so you might be able to guess what this phrase should be. It's not the word vertical that's going to change, because we're still talking about how things are affected vertically. But instead of it being stretched, the opposite of stretch is, there's a couple words for it. You could use the word shrink, or you could use the word compression. And which of those you use might depend on what your teacher or your textbook prefers. So that's actually all of the different things that we can have. That's actually technically not true. That's just all that we're going to do right now. There are also horizontal shrinks and stretches, and there are also reflections across the y-axis, but we're not going to worry about that right now because it adds a level of complexity that I don't think we're quite ready for. So what if we have multiple transformations at the same time? What we have here is called vertex form. And it's called that because the vertex is in our formula, and it's kind of staring us in the face. The alternative to vertex form that we typically see is called standard form, where it just has like an x squared and then an x and then a number, and there's coefficients. And so when it's in that form, it's not telling us anything about the vertex. But here, because of what we just pointed out, this part is telling us that we moved either left or right some value of the opposite of h, basically. This is telling us that we moved up or down. So we've got left or right. It's telling us if it moved up or down. And then we just saw that the number in front tells us if it's been stretched or shrunk. And so put these together, and we can do all three of those things, but also more importantly, it will show us with h and k, whatever those numbers are, it'll show us what the vertex is. Let me show you an example of how that works. And so, because this might seem a little daunting at first, what we're saying. So whenever I see a problem like this, g of x equals 2 times x minus 1 squared minus 3, and it asked me to describe the transformations needed to get the graph of this function from our parent graph, and then graph it, what it wants me to do is say, did it shift left or right? Did it shift up or down? And did it stretch or shrink vertically? And that all depends on if there are numbers in these three places. If there's not all three of those numbers, it's not doing all three of those things. If we want to know if it shifts left or right, we're looking inside of our parentheses. A -1, that's part of the super secret opposite society. So this -1 is telling me that it shifts right 1. The -3 on the outside that I'm subtracting outside my parentheses, that's telling me about up or down. And since it's a -3 and it's outside, which is not a part of the super secret opposite society, that means that I would shift down 3. And then the 2 that's in front is telling me, because it's a whole number that's bigger than 1, it doesn't have to be a whole number, it just has to be a number bigger than 1 on the outside. It's telling me that this is vertically stretched by a factor of 2, or just vertical stretch by 2. So if you wanted to make a table of values for this, what you would want to do is use the fact that we're moving to the right 1 and down 3 to know that your vertex is 1, 3. It's a positive 1 because it's right 1, not left 1. And by picking that as our vertex, by putting that in the middle of our table of values, then we actually know what the best values to plug in will be, because we want to pick things close to our vertex. The other way to do it, if you don't feel like plugging in those numbers, is to say, okay, I know what a parabola, what the parent graph looks like, So this child graph that I have that I'm trying to do, here's my parent graph. The child graph here that I'm trying to do, I'm going to take my points, I'm going to move them right 1 and down 3, and also vertically stretch them by 2. And the vertical stretch is what's going to be a little bit hard here, I think. I think the other two things are pretty easy. Move each point right 1 and then down 3. Here's my vertex. Move the other point. If I move the other points, here they are. Now this isn't going to be correct yet, in case you're like, why are you putting them there? This is if I just move right 1 and down 3. Now if I vertically stretch by 2, I need to make all of the points other than the vertex be twice as far from the vertex than they currently are. So the vertex is where it's supposed to be, but I need to move this point so it's twice as far. So instead of it being 1 away, it needs to be 2 away. And these 2 points, instead of them being 4 away, they need to be 8 away. Now you can do this, you can get the same exact answer, the same exact graph, by plugging in points. You do have to pay attention to order of operations here. It doesn't matter which one you start with, but like if you start with plugging in the 3, what you want to make sure you do is the inside first. 3 minus 1 is 2. Then you want to square 2. Then you want to multiply by this 2 and then subtract 3. So 8 minus 3 is 5. So when I plug in 3, I should get 5, and that is what I had. These are our 2 basic ways, given vertex form, that we can go about trying to graph these functions. And so the only other thing that can happen that didn't happen on that one is we could have a reflection as well. So that happens here on this graph, that we have a negative in front of the 1/2. So that is causing us to reflect across the x-axis. So it's going to make it point down instead of up. Reflect across x-axis. Okay, the 1/2 is going to be a vertical shrink or compression by 1/2. So all of my points are going to be half of the distance away from the vertex that they normally would be. The +3 is part of the super secret opposite society, which means that it's telling me to shift left 3. And then the -1 is telling me to shift down 1. So putting this all together, and it is helpful either to actually graph it on here or just have an idea of what it's supposed to be so you know what you're trying to move. We want to shift left 3 and down 1. So here's where the vertex will be. And then we also need to make it reflect so that it's going down. So that's going to make our points go this way. But it's also, they also need to go half as far from the vertex. So instead of going all the way to 1, I actually just need to go half of a square away from my vertex. And instead of being 4 away like these are, I just need to be 2 away from the vertex, because that's what's half as far. And there's my parabola. It's opening down. It's wider than it normally would be because we've vertically compressed it. So that's my parabola. If you were to use a table of values, the important thing that you take away from the equation is it's the opposite of that 3, which is -3, but it really is -1. So here's our vertex, which tells us what other points would be good to plug in. We'd pick points that are close to -3. I have one more problem here, and so this would be a good time for you to see if this is making sense. So if you would like to pause the video so that you have some time to try to graph this yourself, then please do that now. Okay, so now that you're back, we are going to, I'll just go ahead and tell you what all's going on here so you can check and see if you've got the hang of it. The negative makes us reflect again. The +1 on the inside is part of the super secret opposite society, so that's a shift left 1. The +4 on the outside is not part of the super secret opposite society, so it shifts up 4. And then the 3 is a vertical stretch by 3. So we put all this together, and so if you just checked that and that was wrong and you want to try that part again, then pause the video again. If you are using a table of values for this, what's important here is that we moved left 1 and up 4, so our vertex is -1, 4. So we'd pick things that are close to that to plug in. So -1, 4 is where we're starting. We're opening down, and everything's going to be 3 farther away than normal. So instead of going up 1 over 1 or down 1 over 1, we want to be down 3 over 1. And then instead of being 4 away, we want to be 3 times as far, which is 12 away, which I just barely have room for. And here at the very bottom. And I'll be honest, I don't have a ton of confidence in that. So I would plug in, also that's a terrible looking parabola because it's really hard to draw on a computer. Maybe not really hard, and maybe not for everybody, but it's not really my strong suit, I feel like. If I plug in 1 to check to make sure I put those 2 points at the bottom in the right place, 1 plus 1 is 2, 2 squared is 4, 4 times -3 is -12, and -12 plus 4 is -8. So that is in the right place. I hope you have enjoyed this video on exploring how graphing quadratic functions work. If you did like it, feel free to like and subscribe and do your homework.